the image distance is positive if the image is real. But where would it be formed so that it's real? By a lens. To the right of the lens. Because the light goes through the lens to form the image on the other side. So it will be to the right of the lens. But if it's a mirror, the light hits the mirror, never goes to the other side, and if it forms an image on this side, it's because the light ray is actually bent over there. So it will be to the right of the lens or to the left of the mirror. Doesn't matter if it's concave or convex. Now, when is the image going to be virtual? Well, that means the image distance is negative. When the image is virtual, well, for a lens, the light goes through the lens so it doesn't come back. So if it forms an image on this side, it's because it's a virtual image. So that would be to the left of the lens. Or, well, if it's a mirror and the image is virtual, that means that the light rays are formed, but the light doesn't go to. So it's going to be to the right of the mirror. So this will be here, to the right of the mirror. Convex or concave, it doesn't matter. But you can either memorize this or try to understand it. If you try to understand it, it will be a lot easier. I think a lens, the light comes in, goes through, so it's going to be real on that side. If the image is on that side, it's going to be virtual on this side. For a mirror, the light comes in, hits the mirror, and comes back. If it's real, it's going to have to form the image on this side. And if it's virtual, it has to form the image on the other side where the light doesn't go to. Right? So, just like that. Okay, so what about a convex mirror? Just, to draw some things with a convex mirror. So this is a convex mirror. It bulges on the outside. So what if I draw some ray diagram of an object in front of a convex mirror? So what would happen in that case? Well, let's see. I'm going to consider this. So what if the mirror is like, this is a convex mirror. So the mirror is like this. That's the reflecting side, and this is the object. So I draw the principal axis like this, right? This is the vertex. And, well, light rays are going to be coming in. Well, what's going to happen? It's going to reflect. And it's going to reflect like that, right? Because, the normal to the surface over there, so that's the center of curvature, right? And the focal point is usually like over here. So what about the light ray? If I draw another light ray hitting the vertex, so it's going to hit over there, and then it's just going to reflect, so that this angle is equal to this angle. This angle is equal to that one, right? So I'll make that one. I mean, I didn't do too good of a job over here. Maybe like this. So this angle is equal to this one. Now look at the reflected rays. There is no way, for no position of this object, that these two light rays are ever going to cross. So the image is never going to be real. So this one seems to come from there, and this one from there, so the image is formed right there. So the image would be like over here. Is that image real or virtual? It's virtual. Is it upright or inverted? And that means the magnification is plus, right? And is it enlarged or reduced in size? So that means that the magnification is, less than 1, but more than 0, right? It's positive, but between 0 and 1. By the way, what is the magnification of a flat mirror? Not a curved spherical mirror like this, convex and concave. The flat mirror in the restroom. What is the magnification of that, of a flat mirror? Because consider a flat mirror, not curved. So for a flat mirror, what is the magnification? Positive, negative or positive? Remember what the positive and the negative means.
Positive one?
It is the image that you see of yourself, upright or inverted relative to you. So it's positive. And what's the size of the image relative to your size? The same, actually. So it's +1. So the magnification is +1 for a flat mirror. Yes? And what is the focal length of a flat mirror? Well, think of it like this. Can I erase this part over here now? Okay, think of it like this. Let's sort of take the limit of a concave mirror. Suppose you have a concave mirror like this, curved like that. Where would you say is the focal point? I mean, the center of curvature will be like, if I will continue, center of curvature is like right there, so the focal point will be right there, so this is the focal length, right? Right? What if I make it a little flatter? So if I keep going around like this, right? Center of curvature there, so the focal length is going to be here, so it's going to be longer. What if I make it even flatter? That is like, you have an object like this, is the center curvature, focal length will be here, so F is getting longer. So, and what if I make it, what if I make it flat? Where would the focal point be?
Where the object is? Where the object?
No, the focal length and the focal point is independent of where the object is. Now, I'm not asking for the image. Just where's the focal point? At infinity. It will be like infinitely far away. So this will be at infinity. Right? As you open up this mirror, the focal point moves farther, farther, farther out. And when you make it flat, this thing has gone to infinity. Go back to the definition of the focal point of the mirrors. So what if I apply this equation to a flat mirror? Let me just apply this equation and that equation, right? So notice the following. For a flat mirror, right, the magnification is 1. This means that, well, y prime over y is 1. So this means that the image distance is the same as the object distance. So the image that you see of yourself is just as big as you are. That's because the magnification is 1. The other thing is, what about this one? Right? If I apply 1 over f equals 1 over s plus 1 over s prime, and I make f equal to infinity, this becomes 1 over infinity equals 1 over s plus 1 over s prime. But what is 1 over infinity?
0.
0. And if I solve for s prime over here, what do I get?
Negative s.
Negative s. So that means that the distance of the image from the flat mirror, right, on the other side of, where you think the distance from the image to the flat mirror is the same distance that you are standing in front of the mirror. So if I stand 1 meter away from the mirror, the image is going to be 1 meter away behind. If I stand 2 meters away, then the image is going to be 2 meters away behind. But we are very used to seeing ourselves, just about every day, I think we see ourselves in the mirror, right? And we always see an image that's the same size as we are. And we've been doing that since we were little kids. And so you look at yourself in the mirror, so you stand further away, so you look further away, right? But you know that if you get closer to it, then the image is always the same size as you are. This type of a mirror, the convex mirror, introduces a little problem. Because, first of all, it'll always create an image of the object no matter where the object is. The farther away the object is, the closer this image is going to be to the focal point. And that means it's going to get smaller. So, if the object is closer, the image is going to be here. If the object gets farther away, it'll be there. If it's farther away, it's going to be like that, right? And so this convex mirrors, curved like this, are used on the side mirrors of trucks. And yes. And the problem with those is that if you look at a car on this lane, right, the image of a car on this lane, right, formed by one of these curved mirrors, you see a little car. And your interpretation may be that, oh, I'm looking at a little car, it's got to be far away. But you're looking at a reduced image of the object may not be that far away. So there's always a disclaimer, right? Objects are farther away than they appear. Something like that is what it says in those mirrors. So, something like that, right? Yes, I don't know if you are aware of those, right? Objects are closer than they appear to be, or because they really are closer, right? So because if you look at the rear view mirror like in a car and you see a small car, then you know that car is far away. That's a flat mirror, right? But if you see a car in one of these curved mirrors and it looks small, you might think, oh, it's small because it's far away, because I'm so used to seeing at myself and images of myself or whatever using a flat mirror, not so much this one, so I'm not used to that. So therefore, if it looks small, your brain might say, oh, it's far away, change lanes, when the car might be right there. Yeah, so that's.
So what is the point of using convex mirrors in a car? What's the point of having the convex mirror in the car?
You can always see cars that are far away.
Oh, okay.
Yeah. I mean, the side view mirrors, most of it is flat, but then they'll put something in there to,
Right.
But anyway, they're also used like in the corners of a supermarket, because it'll image anyone walking on the aisle, right? So you can be standing over here, you can look at the mirror. So people will look small, but you can see if someone is like stealing something or whatever, and like over here, right? I can see. Well, I can see Ernesto. I mean, I can see the wall over there. And so anyway, they because they're curved like that, they give you a wide field of view. But for a flat mirror, the image distance is the same as the object distance. Oh, by the way, because the S prime is negative, what happens if I plug it into this formula? Right? Then the magnification, if I use minus S prime over S, if I use 1 over S, and instead of S prime, I plug minus S, then this cancels that, and minus times minus gives me a plus 1. It's like I'm going around in circles, but it's, for a flat mirror, I mean, they're kind of boring. The image is as far from the mirror as the object is from the mirror. It's upright. The image is upright relative to the object. The magnification is 1, so it is not enlarged. It is not reduced. It gets more interesting with the curved mirrors. Okay? It is not good. All right, so those are the sign conventions. I guess I better erase this before it gets too hard to erase.